Astronomers have begun one of the most far-reaching efforts ever undertaken to study the universe. They are forging giant new lenses and mirrors while marshaling vast computational power. These new technologies are at the center of a historic quest to peer into the deepest recesses of time. To find out how the universe set the stage for galaxies and worlds like ours. In an era known as the Cosmic Dawn. Philippe Menenteau and colleagues from the University of Illinois are part of a global push to advance the science of cosmology, the study of the universe as a whole.
Hey, hi guys.
They are mapping the positions of galaxies across the sky and extending deep into the universe.
Oh yeah, that doesn't look good.
Yeah, no.
So that was only at the end. Can you
Their goal,
show us something
to link the evolution of
how it was
planets,
looking when it was good.
stars, and
That's
galaxies,
clearly something out
the
there
universe
with
we
this
see
stuff
around
is
us,
working out.
with conditions that existed at the dawn of time.
That is because it's in a corner. Those is because those are corners.
What forces came together to form the very first generation of stars and galaxies? And over time, the vast architecture of matter and light we see in our telescopes. Only a century ago, astronomers debated whether the universe is confined to a giant rotating disk of stars, dust, and gas, the Milky Way, or whether our galaxy is one of many so-called island universes. We now know that our galaxy is part of a formation of 3 major galaxies, along with some 51 dwarf galaxies called the local group. The local group is bound by gravity to a much larger formation, the Virgo cluster, with up to 2,000 galaxies. Beyond Virgo, galaxy clusters are linked to superclusters in a pattern laid out by the first great cosmic mapping project, the Sloan Digital Sky Survey, beginning in the year 2000. As the Sloan data shows, superclusters are connected to each other by streams or filaments of galaxies, bounded by immense empty regions. To understand how the universe got this way, astronomers must identify its basic components of matter and energy. Back in the 1930s, the astronomer Fritz Zwicky measured the rotation rate of spiral galaxies like the Milky Way. He found that the gravity that binds their stars is over 100 times greater than what he expected, based on the amount of matter that's visible. Zwicky called the unseen substance exerting this extra gravitational pull dark matter. You can see its influence on even larger scales. Without dark matter, the gravity of clusters like this is not enough to hold all the galaxies rotating around it. In this case, dark matter acts as a lens, magnifying and distorting the light of galaxies in the deep background and causing them to appear as blue arcs. Astronomers use the pattern of gravitational lensing to map the distribution of dark matter in the supercluster Abell 1689, shown here as a blue haze. On a large scale, galaxy structures like these are a measure of how much dark matter there is.
One of the tools that we have in cosmology to pin down the kind of universe that we live in is the growth of the structures. These are giant systems with hundreds of thousands of galaxies. And these systems, these ones that are particularly big, are very, very rare. And the number of those that you can find as a function of cosmic time, from here to the past, depends. It's a very strong prediction of the universe that we live on.
This computer model shows the role dark matter has played in shaping the contours of the universe. Not long after the Big Bang, gravity began to amplify slight initial variations in the distribution of dark matter. Regions of the highest density attracted enough visible matter to form galaxy clusters and the largest superclusters. Even as astronomers struggled to define what dark matter is, they discovered another mysterious and powerful influence on cosmic evolution. In the late 1990s, two groups of astronomers asked whether there's enough dark matter out there to one day slow or even halt the expansion of the universe. Using the Hubble Space Telescope, along with ground-based telescopes, the team set out to track the rate of cosmic expansion through the entire history of the universe. They did this by searching deep space for a particular type of exploding star. Called a Type 1a supernova, it often begins with two stars in a close orbit, one of which draws gas from its companion. When it gains enough mass, it undergoes a runaway nuclear reaction and explodes. Because Type 1a supernovae are all thought to blow up in the same way, they have the same intrinsic brightness. That makes them ideal for measuring cosmic distances. It's like looking at car headlights approaching on a highway. The dimmer they appear, the farther away they are. The astronomers combined distance measurements with another marker, how far their light had shifted toward the red part of the light spectrum. The greater this redshift, the more the universe had expanded since the star exploded. Some explosions appeared dimmer than the teams expected based on their redshift. That meant their light had traveled farther than it should have, given a constant rate of expansion. This finding led the two teams to conclude that in the deep past, the universe was slowing down. But to reach its current size, it must have then sped up. Scientists now believe the universe is dominated not by matter we can see, nor by the mysterious gravitational presence, dark matter. It's something else, pervasive and powerful enough to cause space to accelerate outward. They call it dark energy. One leading idea is that it stems from particles that well up from the vacuum of space. As the universe expands, it generates more and more dark energy. That has the effect, over large distances, of counteracting gravity and causing space to expand even faster. Spread over the vastness of the universe, it is the energy equivalent of only 5 hydrogen atoms per cubic meter. And yet scientists find that dark energy accounts for 68% of the entire cosmic matter energy budget, with dark matter at 27% and ordinary visible matter less than 5%. The twin discoveries of dark matter and dark energy have thrown cosmology into turmoil and potentially into a new age of discovery. Astronomers have now launched a full-scale effort to pin down the forces and events that drove cosmic evolution, going back to the earliest times. Already, a fleet of space telescopes led by Hubble is scanning the distant universe for light sources across the electromagnetic spectrum. The long-awaited James Webb Space Telescope, slated for launch in 2018, represents the next generation of great space observatories. With a segmented primary mirror that is almost 3 times larger than that of Hubble, the James Webb will capture the trickle of photons from a time nearly 13 billion years ago, when the universe lit up with stars and galaxies. The next generation of ground telescopes will radically extend our light-gathering power. The European Extremely Large Telescope, now under construction in Chile's Atacama Desert, will have a 39-meter mirror that quadruples the light-gathering power of the largest telescopes today. While these telescopes extend our vision into the deep universe, the American W1 and European Euclid space telescopes will take in large regions of the sky at high resolution. These new instruments, each slated for launch in the 2020s, will be used to survey the deep universe for Type 1a supernovae and other markers of cosmic evolution. These space observatories will work in conjunction with an ambitious new effort to track the evolution of the cosmos in near real time. The Large Synoptic Survey Telescope, or LSST, is being built in the mountains of Chile. It combines data gathering on an unprecedented scale with plans for dedicated fiber optic connections capable of delivering a flood of data to supercomputers a continent away. From there, it will be processed and made available through advanced internet links to scientists around the world. At its heart, the LSST will be outfitted with the largest digital camera ever built.
I don't see any sleeps.
That includes the largest lens ever built, now undergoing final polish before assembly.
Good, huh? Yeah.
With a field of view the size of 50 full moons, the telescope will observe just over half the sky visible from the Earth, to a depth of about halfway back to the beginning of time.
LSST is going to take a new image of the sky in roughly every 47 seconds. And so for us to bring the picture of the sky to the world as quickly as possible, we are going to release a catalog of how the universe appears to have changed with time within 1 minute of that shutter closing. And so every 47 seconds, every night for 10 years, we're going to distribute effectively a mini worldwide data release of how the sky looks like it changed with time. And on average, LSST will image the entire southern sky roughly once every several days.
Astronomers expect the telescope to record a blizzard of transient events, from asteroids buzzing through the solar system to black holes flaring up in distant galaxies and stars exploding out on the horizons of space and time. The telescope will revolutionize what scientists call time domain astronomy.
Right now, there are lots of time domain surveys going on, and worldwide you might get thousands of new alerts per night of things that have changed in the sky. But LSST will change that. It is so much bigger and samples such a larger volume of space that it will have 10 million new things every night that it looks at the sky. That's 10 million every night for 10 years. And so suddenly it's a whole different ballgame, right? The scale is well beyond anything that has ever happened in time domain astronomy. It opens up space that we've never explored before.
To make sense of the deluge of data, this project will make extensive use of supercomputer models designed to simulate periods in cosmic history. These powerful programs are based on theories of star and galaxy formation, the influence of dark matter and dark energy, and a host of other parameters. Scientists will use them to test theories about what drives cosmic evolution by comparing simulation results with data captured by the telescope.
These data sets are so complex that we really need simulations of cosmic evolution to even understand and analyze the data, let alone interpret them. The computations really translate our theories of dark energy, dark matter, cosmic evolution into observables that we can then go out and test with our observations.
The LSST project will build upon previous large-scale cosmic surveys. The Sloan Digital Sky Survey has mapped galaxies out to 1/3 the distance to our visible horizon. Astronomers are now leaping beyond that with a project based on a summit across the canyon from LSST. It's called the Dark Energy Survey. Here, at a dedicated 4-meter telescope, Felipe Menento and colleagues are pioneering new systems and procedures for mining the light of deep space.
515473.
515473?
Yeah.
Because of the time it takes for the light of distant objects to reach us,
No.
when these astronomers look deep into the cosmos, they are looking back in time.
We are looking back in time, kind of like an archaeologist, like digging deeper into the ground. And at each one of these epochs, we are kind of like seeing the relic, the fossils that were left. So we cannot follow a galaxy back in time, but we can actually take snapshots of populations at different cosmic times and see how they have been changing since early on until today.
Yeah, but the thing is that, under this, there are...
That's 2012B.
No, you're not that. You're like 2016A.
The telescope captures the light of stars and galaxies across the electromagnetic spectrum, from high-energy ultraviolet to low-energy infrared. These colors reveal important galaxy characteristics, such as the rate of star birth, the amount of dust or gas within them, their distance from Earth. The camera's sensor divides the field of view into 62 high-resolution detectors. Each one captures countless thousands of celestial objects, some bright and well-known, others too subtle to see with your eye. Night after night, month after month, the exposures pile up across a survey area that covers 1/4 of the southern sky, or 1/8 of the entire sky as seen from Earth. With data from the Dark Energy Survey combined with a much larger LSST survey, scientists will create a three-dimensional map of galaxies going back to when the universe was half its current age.
We only understood that we live in a universe full of galaxies in 1930s. Before that, we didn't understand our place in the universe. And since then, there's been this constant quest to understand why galaxies look the way they look. How did they form? And how this process has been shaping also, the planets, the stars, everything that it's in them. Because, galaxies are the building blocks of the universe.
In recent years, advanced telescopes have shown that the universe is filled with galaxies in a wide variety of shapes and sizes. From giant spheres of ancient dying stars to complex, twisted shapes, often run through with rings of dust. The historic Hubble Deep Field took us back for the first time to the early stages of galaxy formation. It found that blurry scraps of stars and gas visible at the dark margins of space are primitive galaxies. Theory says they will one day merge into larger, mature galaxies.
Something that astronomy has been trying to answer for decades, particularly after the Hubble Space Telescope was in space and we were able to see with amazing precision the morphology and the shapes of the earliest galaxies in the universe. We've been trying to answer and trying to connect morphology and colors with the evolutionary stage of the galaxies.
Okay, you have this kind of galaxy and that kind of galaxy. How do they fit together? Or do they fit together? Does that galaxy turn into this galaxy or the other way around? Does this kind of galaxy never become that kind of galaxy because it didn't have the right nurturing or the right environment? If you were an alien coming down with no knowledge of how humans work, and you landed in a city, and you were just walking around looking at some city blocks, you would see all kinds of different people. You'd see babies, and you'd see old people, and you'd see teenagers and people in their mid-20s, but you wouldn't necessarily have an idea of how all those people fit together. Do people just arrive at these different stages, or are they working through some evolutionary process? So it's the science that lets you understand that, things are evolving. So you have a baby that then grows to a toddler, that grows to a teenager, that, eventually becomes an old person.
Using the ALMA telescope array in Chile, astronomers caught a glimpse of galaxy evolution in its earliest stages. They focused the telescope on the southern constellation of Cetus, setting their sights on a seemingly empty region. Deep within it, about 3.5 billion light-years from Earth, lies the galaxy cluster Abell 2744. It's known as Pandora's cluster for the tangle of shapes created when at least 4 smaller galaxy clusters merge together. To one side, astronomers found a faint, ghostly shape that had been magnified by dark matter within the cluster. It is a pocket of stars, far beyond and much older than the galaxy cluster. The stars were being born when the universe was just 600 million years old. This animation recreates the ancient star cluster, surrounded by gas and punctuated with supernovae. Over time, most star clusters like this would have merged with a galaxy. As it turns out, a small number have managed to stay intact over the billions of years since they were born. Finding them within their original dark matter cocoons has become a passion for these members of the Dark Energy Survey, Alex Derlika-Wagner and Keith Bechtel.
There are expectations from this model of galaxy formation for the existence of many of these small dark matter clumps in the halo of the Milky Way. And so while this was an expectation that was put forth, basically from simulations, there were very firm predictions about if this paradigm were correct, how many dwarf galaxies DES should find.
Astronomers have long known that the Milky Way galaxy is enveloped in a diffuse halo of stars, including some 160 large star clusters. M15 is one of the densest known. Gravitational interactions among its stars have caused them to pack in tightly. So-called globular clusters like this are like pottery shards found by archaeologists at the sites of ancient villages. One, called Turzan 5, has even managed to survive a fall into our Milky Way. It contains a population of relatively metal-poor stars that would have been born 12 billion years ago. There should be many more clusters like these, in a wide variety of sizes, that have simply not had time to enter the disk. Where are they today? When the first round of data from the Dark Energy Survey was released, Alex and Keith began combing it for light that could be resolved as stars. They saw what they were looking for. Tiny remnants of the Milky Way's birth, star clusters almost entirely devoid of metal content. These dwarf galaxies turned out to be dark matter rich, with about 10 times the ratio of dark to visible matter as seen in the galaxy as a whole.
We have this idea that galaxies form from the bottom up, many, many small galaxies, and then, over billions of years, they merge together to form larger galaxies. What this means is that the smallest galaxies were also the first galaxies, and therefore they're the oldest. And when you actually look at these dwarf galaxies and you study the properties of their stars, you find that the stars are very, very old, that most of them formed over 10 billion years ago.
This realization is central to cosmology's quest to link the early stages and growth of galaxies to cosmic evolution on the largest scales. That quest points to the ingredients of matter and energy that produced the very first stars at the cosmic dawn.
Immediately after the Big Bang, the universe was hot and very, very, very homogeneous, but it wasn't perfectly homogeneous.
In fact, astronomers have found a telltale pattern in light emitted when the universe was just 300,000 years old, the so-called cosmic microwave background. In this image from the European Planck satellite, the colors indicate hot and cold patches produced by tiny variations in the energy of the Big Bang.
These small fluctuations, these small variations of matter then got amplified by gravity. And these tiny variations, this tiny clumping of matter were the seeds of the galaxies that we see today. And this is crucial. The amount of variation that we saw early in the universe predicts, together with all of the other ingredients that we need for a universe, predict the rate in which the structures are growing, meaning the number of clusters of galaxies, the number of superclusters, the shapes of the cosmic wave is determined by that initial imprint.
To trace the evolution of this imprint, scientists are using a supercomputer model to recreate the eruption of stars and galaxies in the cosmic dawn. It begins in the darkness of the early universe, barely 6 million years after the Big Bang. Gravity draws dark matter into diffuse halos. Within them, hydrogen gas forms clouds that become more and more dense over time. As gravity compresses the clouds, they begin to heat up, then finally ignite to form the first generation of stars. These stars are giants, much larger than any today. One blows up in a powerful supernova. The model shows an environment transformed by the explosion. The supernova litters its surroundings with heavier elements created in nuclear fusion. Carbon, silicon, iron, and more. These so-called metals cause surrounding clouds of hydrogen to cool. That allows them to collapse. Turbulence breaks them into smaller pockets. A cluster of smaller second-generation stars now begins to form. Here's a wider view of the scene almost 400 million years later. From data generated by the simulation, scientists are working to isolate the dynamics of galaxy evolution. Stars are being born where filaments of gas, shown in blue, come together. Ultraviolet light from these stars begins to strip electrons from hydrogen atoms in a process called ionization. That causes surrounding regions to glow with visible light. The ionized gas appears as bubbles. They're associated with pockets of elevated temperatures, shown in red, as well as high concentrations of metals spread by supernovae, shown in green. The simulation reveals a dynamic that shaped the course of cosmic history. Heating from ionization tends to push the gas out. That suppresses the rate of star birth. Metals, on the other hand, allow pockets of gas to cool and fall inward. That increases the rate of star birth. So instead of stars forming and collapsing immediately into galaxies, the universe becomes a wide mix of hot and cold regions, large and small star clusters, and pockets of gas amid clouds of dust rich in metals. The small dwarf galaxies that astronomers have spotted hovering above the Milky Way are relics of this early period and of the galaxy's early years.
The formation of the first generation of stars, also referred to as population 3 stars, were these very massive stars to form early in the universe, polluting the intergalactic medium and the interstellar medium with unique chemical fingerprints of their own formation, different than the sorts of supernovae that we see today. And ultra-faint dwarf galaxies, we have evidence that many of them are actually fossils of this era of reionization, where some of them are thought to have formed before reionization took place. And we also have evidence from the chemical abundances of stars in the ultra-faint dwarf galaxies that the chemicals that they were enriched with may have been coming from that first generation of stars itself.
The supercomputer model gives us a view of cosmic evolution advancing to an age of about 1 billion years. The scene is dominated by star birth and by star clusters merging together into larger formations. The universe continues to put the brakes on galaxy growth. While star birth spreads heat, stifling the flow of gas into galaxies, metals from stars and supernovae have a cooling effect that enables this flow. Many of these early generation galaxies join in larger aggregations. Take the Spiderweb galaxy, 10.6 billion light-years away. A close examination shows that it sits in the middle of a cluster of galaxy fragments. This animated reconstruction shows the chaotic scene. Hundreds of small galaxies and patches of stars are interacting while drawing in matter from the surrounding region. Starting in the early years of the cosmic dawn, this simulation shows a slice of the universe in a region 350 million light-years across. The gravity of dark matter gradually concentrated visible matter into galaxy clusters. At the centers of large galaxies, black holes grew to supermassive proportions. As matter flowed in, they generated immense expanding bubbles of gas. These bubbles pushed beyond their galaxies, spreading waves of hot gas. The heating from these bubbles would slow the flow of gas into the clusters. That allowed smaller galaxies like ours to form on the margins. At the same time, black hole winds seeded the wider universe with dust and metals generated by supernovae. Flash forward to the present era. Our galaxy has by no means completed its evolution. This simulation recreates the last 60 million years of its history. Within the disk, each flash of light is a supernova. As time goes by, Thousands upon thousands of these explosions seed the galaxy with metals, the cosmic dust from which new generations of stars and solar systems are born. Though most of the Milky Way's stars reside within the disk, some orbit far above or below it in the galaxy's halo and occasionally pass through the disk. Our galaxy today is the product of countless small and large mergers going all the way back to the early universe. Its landscapes are the ever-evolving product of star birth and star death. The Milky Way is filled with some 200 billion stars born at each stage in the life of the cosmos. They are intermixed with clouds of dust and gas, all swirling around a bright central region called the bulge. We glimpse its origins within a halo of stars and small clusters, some nearly as old as the universe. From our vantage on Earth, the universe continues to reinvent itself.
Okay. Así que vamos a hacer star plots.
A supernova's light has just reached Earth from a nearby galaxy called Centaurus A.
Not right now, it's taking an exposure.
Okay,
so
yeah, let's finish that one.
It's of particular interest to the astronomers. Its interaction with surrounding dust clouds can reveal the environment in which its parent star lived and died.
If you're a physicist, you have a lab, and in your lab you can change the parameters of your experiment and keep testing it. When you are an astronomer, you cannot create stars, you cannot create galaxies. The universe is your lab, and you are a humble collector of light.
Try 515473.
515473?
Yeah.
Okay.
Day by day, month by month, the light of the universe rolls into the data pipeline. Here is one slice of the southern sky from the Dark Energy Survey, extending roughly half the distance to the edge of our visible horizon. It's just the beginning of a grand cosmic census that includes galaxy clusters, galaxy types, rates of star birth, chemical abundances, distances from Earth, and more. When the data from this and the Large Synoptic Survey are combined and laid out in time, they promise a record of how the universe evolved since its early moments.
It is just jaw-dropping to me that humans can even undertake these big questions and figure out where we are in the universe. And as we see the universe changing with time over the last 13.7 billion years, it gives us a sense of the cosmic structure formation events that have ultimately led to systems like the sun being formed.
Discovering the shapes and contours of the universe is only the first step in understanding how it came to be. Astronomers will sift the data for clues to the initial conditions that came together in the cosmic dawn. They'll test theories about the identity of dark matter and dark energy.
But there is also even this more fundamental question, which is, do these things even exist? I think the evidence for dark matter is quite strong. We see it really explains a number of different phenomena. Dark energy, I think, is our best current hypothesis for what It's causing the universe to speed up. But it's still on, I would say, shaky ground. Is dark energy just the energy of empty space? Or is it the energy associated with some new fundamental particle in the universe?
Assuming current observations hold up, astronomers in the distant future may produce a very different cosmic map, one that reflects a universe pushed further apart by dark energy. Many of the galaxies we see today will have receded beyond our horizons, becoming invisible from Earth. Our own Milky Way will remain intact, still enveloped in the dark matter that spawned it. Its halo will become increasingly entwined with that of the Andromeda Galaxy, our larger neighbor. It is now moving toward us at about 400,000 kilometers per hour. When the two meet, several billion years from now, their interaction will dominate our night skies. From a point of view unique to their time, those future astronomers will look out at the horizon and ask, how did it all come to be? Where does it end? We ask the same questions today based on our point of view at this moment in cosmic history. Our technologies are allowing us to see nearly to the beginning of time and to track the behavior of the universe on the largest of scales. And yet, the more we see, the deeper the mysteries become.